So, welcome back. I know we're saying this is part seven, but it's really kind of part two or part B to the last part, part six of the course, where we're talking about discovery and collection. I warned you in the beginning of the last one where it's one of my favorite parts of the course, and there's just so much to talk about. Of course, we're talking a lot about finding the assets in the environment, right? The relationships between those assets and how they control the equipment, the process out in the real world, right? How are they programmed to do what they do? So we can reverse engineer the environment to understand how we can have an impact. So we're taking our time, a lot of time, right, going through these sections, and then we'll be able to go quicker through later parts of the course. That's the idea. So this is really, welcome to part seven. Remember, this is a continuation of discovery and collection. So again, this is part seven in the course, but it's really a continuation of the last part where we're talking about discovery and collection. Remember, understanding the different OT or ICS assets like PLCs and HMIs that are on the network and the relationships between them. And as we learn those relationships, we also start to learn, right, how these OT and ICS assets control the process, right? Control the equipment out in the real world. So we have a lot more to talk about. Now we're also at the halfway point of the course. So if you made it this far, congratulations. I know it's been a lot and we're only at the halfway point, but hopefully you're excited about this information and it's probably that's why you're here. So real quickly, I did want to go through just a couple of kind of review points, right? Why are we here? Why was I taking the time to put this class together? So remember, we're not prepared as a whole for those of us defending OT or ICS environments. We're not prepared for the attacks that are going to be coming. We're not prepared for the attacks that are happening today. We're not. I hate to say. But one of the best ways that we can learn to become prepared is to learn how attackers break in to OT environments. And then, of course, once they're inside, then what do? Right? We're walking through that process of, okay, we got the foothold on the network. Then how do we find the different control systems? How do you find the equipment and the process in the real world that they monitor and control? And how do they do that? Right, so we can reverse engineer the process as a pen tester or as an attacker to then understand what changes we can make to have the most impact in the environment. Now, of course, attackers, they have multiple ways to get into OT networks. Right? And then once we're in, there's multiple ways to have an impact. It's just a matter of what we want that impact to be and how impactful, right? Do we want it like a real small, minor impact, or do we want it something that the whole world will stand up and take notice of, or somewhere in between? But hopefully, one of the things that I've started to be able to show you in this course is that we don't have to design these complex or complicated attacks or tools to have an impact in the environment. We don't, not any longer. Now, of course, a lot of folks still don't know that in OT environments, we have so many Windows systems, domain controllers for Active Directory and file servers and data historians that are running on Windows, right? Our engineering workstations that we use for things like programming PLCs are all running Windows. So if you're a pen tester or an attacker that already knows how to gain access and move from Windows machine to Windows machine, you already have a good understanding of how to compromise a significant portion of an OT network. Right? As we talk about moving, especially from Windows machine to Windows machines, or we talk about commodity operating systems. And sure, remember there's maybe some Linux a little bit in there that we call those phase one attacks. Phase two attacks are what we focus on in this course. So we assume that you're already on the OT network, that you already have that foothold, you already have full control over all the Windows-based systems, at least those that are in the Active Directory domain for the OT network. Of course, we always talk about how I can never suggest or recommend that you do pen testing in a production environment. And some people do, right? And some people have issues when they do that. So that's between you and your client. I can just never make that suggestion. And then a few last points just to wrap this up, right? Is the idea that the pen test methodology that I follow and that I think a lot of others do is very similar to the process that we see in IT pen testing. And whether that's all the work that we do before the testing or after the testing, like when writing the report and presenting the results to the client, or even a lot of the steps in between when we're actually doing the testing, we're actually doing the fun stuff. It's very similar in an approach to that flow or that methodology that we would use in IT pen tests as well. But obviously, there's going to be some substantial differences because there are some substantial differences between IT and OT environments. Just remember they have more in common than they don't. Of course, when we say OT pen test, or that's why it's here in quotes, the vast majority of OT pen tests that pen testers are actually hired to do by clients are not actually OT pen tests, meaning, right, we're not touching any OT or ICS assets like PLCs, the DCS, HMIs, and RTU. You're only moving from Windows machine to Windows machine 90, let's say, percent of the time. Where typically it's that assumed breach scenario. So you start off in the IT environment with a foothold on a Windows machine, and then the client wants to see, can you get into the IT OT DMC? Can you get a foothold there? And then maybe can you get to a Windows machine inside the OT network? And that's the majority of quote unquote OT pen test. So sure, you're in the OT network, but you're not actually touching any OT or ICS assets. It's still very much a phase one attack, but that's the majority of OT pen tests that environments are paying for. Because they also are concerned with safety and availability issues, and they don't want you to crash the plant. But part of the reason why I wanted to put this course together is that there's not a lot of resources out there to help us understand how to do not only pen tests, but again, I'm looking at learning pen testing in an OT as a way to, hey, this helps me become a better defender. And there just aren't a lot of resources out there. So there's a lot of, kind of the highlights of what we had covered in the first, day of the course. That's the first 6 parts is all of what we consider day 1, right? The first half. And then, of course, we have the OT pen tester methodology itself. Our pre-engagement, what we do before the fun stuff. Post-engagement, what we do after, working with the clients, right before and after. And then the actual fun stuff, right? Doing the actual testing to where we can reverse engineer the environment and determine how we as an attacker could have an impact in the environment. So then we can help the client understand the different risk that exist and how they can at least limit that risk by doing things like implementing compensating controls. So that's the review for the first part of the course. Now, as a review for kind of that halfway point, there is Lab 6.6, right? And what you'll see that I've created a simple scenario similar to the one we used with the air conditioning unit example, right? Very similar. In this case, though, we have a water tank. And so with that water tank, right, there's a couple of questions that you answer, right? So at what percentage of the water tank level will the alarm trigger for the level being too high? Which coil or register controls if the heater is on or off? And then can you manipulate that to turn the heater for the water tank on or off? I also mentioned, well, which coil or register displays the barometric pressure inside the tank? And so you'll also, well, can we read those registers and determine, of course, comparing those values to the HMI, which is the appropriate coil or register? Even just knowing at this point, is it going to be in a coil or a register? If you can remember that, you're already halfway there. Because remember, coils only store zeros and ones. If you need to store higher values, like the barometric pressure inside a tank, that's going to more than likely, at least at some point, be higher than a 0 or a 1, then you're going to need to store it in a register. And so this is what the tank looks like. Nothing special, right? But you can see there's an intake. So when you turn that in, you have water coming in. There's an outtake. So if you turn that on, there's water going out. You can see the flow, how much water is coming in, how much water is going out, right? How fast. You can see the barometric pressure that we were talking about, right? That we're going to look for. And then we can see the temperature inside the tank. Remember, we have that ability to turn on and off the heater. And then there's actually some alarms. We're going to be working with alarms a lot more in the second half of this course. For those alarms that go off to get the operator's attention. Sometimes it's just a visual indicator, right? Maybe the screen's flashing at us. And then if we really need to get your attention, we're going to start screaming at you and have some sirens going off. So let's get back to the OT pen tester methodology. Remember, we're talking about discovery here, or really it's even discovery and collection. Right? Finding out what's in the environment, right? And how those systems are related, right? How do they monitor, control the process and the equipment out in the real world? Now, I did want to make sure, I know this makes this section even larger, is that we did talk about wireless attacks. So we don't have, I was trying to find a better place in the course where I wanted to at least introduce the concept of wireless attacks in OT and ICS. I think it could be its own course, but I did want to make sure we took some time to talk about them. And then you can see some of the other different techniques that we're going to talk about for collection and discovery. Again, some of these that are going to come back when we're later on looking at different attacks on how to have an impact in the environment. So looking at the operating mode of controllers like PLCs, how do we manipulate the data in memory, or talk about that IO image, right? The input, the output. How do we manipulate the data values in memory of a controller? How do we monitor the state of a process in the real world, right? What's happening? And these are all steps that we need to take to be able to reverse engineer the process. And then we can also talk about how they talk about program download. What this actually means is essentially we're going to either upload, or this is where, OT ICS gets a little, they use different terms than we have in let's say in the IT world. So when you say program download, what they're meaning is we're going to put new PLC programming logic on a controller, on a PLC. Or you might say like firmware download, right? In IT, I might think, I'm going to download it to my computer. When you say program download in OT, we're talking about, we're going to put that firmware, that new version of firmware onto the PLC. Yeah, so I try to avoid using download and upload because I get confused because having been in IT for so long, right? And then still, 10 plus years working in OT, but it still can get confusing, and especially for those of you that are kind of new to the field. So I'll say we're going to put it on, or we're going to take it off, right? Not, download or upload. So I talk about wireless attacks. Now, I will say one thing. This is one of those things for me coming from an IT background originally, is that I would always say, well, wireless, that's Wi-Fi. But we have to remember there's other types of wireless besides Wi-Fi. And so we're going to talk a little bit about that in this section. Now, when we go back and we look at our attack timeline, right? Looking at back over time, really the first known, in this case of like say a malicious insider in OT. This actually occurred. This is one of the first OT ICS incidents, period, that had an impact in an environment. And this is where you had basically an ex consultant, right? Used to work for the department that was concerned with sewage down in a township in New Zealand. And this gentleman, he didn't have his contract renewed, I guess how the story goes. And he was very upset by that. And so when he left and was no longer working with the organization responsible for the water treatment and sewage, that he had stolen radio equipment that would allow him to connect into their different pumping stations, and where he could act as essentially the master server, and he could issue commands to these stations, which would allow him to do things like release sewage into streets or creeks and little rivers that they had. So anywhere there was a place where he could actually have sewage coming out into like the general population areas, that he would drive around and do that. And he did that for quite some time. And the police ended up catching him just on a random traffic stop and saw all of this radio equipment in the back of the car. I was like, what are you doing with all of this? So we talk about Marucci Shire, which is interesting because, again, it was not only a disgruntled employee that understood how the environment worked. So he had that specialized insider knowledge, but he had also stolen specialized equipment that he could use as he just drove around town to connect into these pumping stations to be able to do things like open up gates and release sewage into creeks and into streets. So it's a really interesting case. Was there significant damage? There was an impact, and that was really annoying, and you would definitely not want to go through the cleanup. And it was, again, I think really it was kind of like by luck they actually caught them to actually put a stop to those different types of attacks. But with wireless, right, you can have an attacker anywhere. They don't have to physically be on site. They have to be somewhat close-ish, but they don't have to be on site. And again, this is where we saw that disgruntled employee driving around using wireless equipment to release sewage out into public places. Oh, and I forgot, yes, the grounds of the Hyatt Regency Hotel. Yeah, not so fun, right? Millions of liters of raw sewage in all of these different places. So we have wireless, and we use it more and more in OT. I remember, I think even in my first plant back in 2012, there was still, definitely Wi-Fi. They had some minor forms of wireless communication. And then every site I went to after that, of course, yes, there's always Wi-Fi, but there's other types of wireless in the environment. And over the last, 10, 15 years, we've just seen this idea of, tablets for on-site personnel, or even being able to connect devices from your phones over wireless protocols like Bluetooth have just exploded over time. You can have engineering, workstations, right, that are just laptops. And what if you could connect to to Wi-Fi, and what if a PLC was on that Wi-Fi network? You don't see that as much, but you can. A lot of PLCs now come with Wi-Fi capabilities. Now, there's a lot of environments, especially larger environments, or where there's a lot of steel, there's a lot of piping, or even sometimes different maybe distances, right, that make it difficult to run cables. So it becomes too difficult, or it becomes really too cost prohibitive, right? It just costs too much. Where you actually see that it's much less expensive to use some type of wireless communication. So I worked in a steel mill that was a huge facility. And there was basically a river that ran between the middle of the steel mill. And to be able to connect both sides, it was like, well, we can try to run fiber through a channel, maybe, find a way to protect the fiber as it goes over the river. We could run it under the river. That would be very costly. Or if we have some type of wireless connection between both sides of the factory. I start to look at some, field instrumentation we talk about, or things like, remember, like sensors now have wireless capabilities. So you don't have to run cables, right? You don't have to have physical wires. And then the nice thing is, what if we want, instead of having just one sensor out in the field, and what if there's a problem with that sensor, or that sensor crashes or dies? Well, then we're blind for whatever the sensor was monitoring. Well, that's why we can have two sensors. But if I have two sensors, or any unit, right, or any system for redundancy, right, then I have to have two cables, two wires. Well, if it's wireless, don't have to worry about it. Now, there are risks. Now, some of these risks aren't directly related to wireless per se, but if you're sending traffic over a wireless network, if you're sending unencrypted traffic and your wireless network, or the path that the wireless traffic is taking, we'll leave it at that, is going to be unencrypted, right? Somebody could intercept that traffic and read it. Now, we also look at, if you implement wireless technology like Wi-Fi, then of course you inherit all of those vulnerabilities or those risks. So I talk about things like your SSID is going to essentially be exposed. You could hide it, but there you're trying to hide something they're going to find anyways. We'll talk about those in a few. Like rogue access points, somebody actually spinning up an access point and pretending to be a legitimate access point to get people to connect to it and then intercept their traffic. Or what if we have attackers joining their devices to our wireless networks or to our Wi-Fi networks? Right? There's ways to jam wireless communication, right? Generate interference. So essentially those networks and wireless transmission, so quote unquote lines, right? They come down. Well, if you lose all that wireless connectivity, well, now we just think of just like if our wired network went down, we just lost the ability to monitor what's going on in the environment. We just lost our ability to interact with those systems for control. You can see, especially when there's unencrypted traffic, you also have the ability to do replay attacks. So if I can capture a command going over that wireless path, I can capture it, I could replay it. So let's say I capture the command to turn on a construction crane, and then the command to turn it off, and the command to raise or lower the boom. That's the right word. I'll have to look at that one. I think I climbed up a crane one time like 20 years ago. It was one of the scariest things I've ever done. But the idea is if I capture those commands, right, I can just replay them to reissue the command. So then I could, turn on the crane, turn off the crane, lower the crane, raise it, lower it, turn left 90 degrees, turn right 90 degrees. Just by capturing that traffic, we'll actually play with some replay commands or replay attacks later in this course. Right, so there's lots of issues we have. These are just some that are associated with wireless communication. Again, some of these you'll see definitely more in like Wi-Fi, like rogue access points. And then we can talk about there's different wireless protocols that we use, like, sure, we're just talking, of course, Wi-Fi. So we see it everywhere in IT. We also see it everywhere in OT. And a lot of times in OT, it's not as secure as it could be. Not like in IT. I go into a lot of environments. They might be in the middle of nowhere, at least 500 miles from civilization. I say, we don't have to worry about securing it because nobody's going to come out here and jump on our Wi-Fi network. Actually, they will. They will. So you need to secure it. And then we can talk about things like Bluetooth and wireless HART. Or Wi-Fi is what we've inherited from IT. Again, we have to make sure that it's secure. We still take the same steps. If you've never seen wiggle.net, it's actually a really cool site where you can join. And what happens is that people will drive around, right, using the Wiggle app, and they're recording all the wireless networks that they find. And so if they're driving by industrial facilities, like let's say manufacturing sites in manufacturing plants in a city, and that manufacturing plant is using Wi-Fi. If their Wiggle app detected that Wi-Fi access point, it gets uploaded to the website. So you can actually go in and look at the map and see if your target environment, like a manufacturing plant, actually has Wi-Fi and what those Wi-Fi access points, what the SSID is. It's really interesting from a reconnaissance perspective. And one client that I had had 100 plants across the world. And if you find the Wi-Fi, the SSID, right, the Wi-Fi network name for one, they use the same Wi-Fi network name for all of their plants. So you see, sure, here's the plant, let's say in Greenville, South Carolina, but here's the plant in up in Calgary in Canada. And here's the one down in Brazil. And then here's the one in Germany. And here's the one in Singapore. So it's really an interesting tool when you're talking about just tracking Wi-Fi access points. But I always find it interesting when you can see those Wi-Fi networks, right? Those SSIDs associated with OT environments. You don't see them all the time. And a lot of times, right, OT environments are kind of out away from civilization. So nobody's driving out to that power plant that's 30 minutes from anything. So you're not going to have those listed here. But if you have those industrial sites, especially in city limits, usually, and they're running Wi-Fi, you'll actually see them listed on wiggle.net. Here's a little bit of a closer look. You see, it's kind of still very kind of outdated. The other thing is I couldn't really, when you create a new account, you don't really get a lot of access, but you get more access as time goes on. And I think it's also to help kind of persuade you to install the app and drive around and record Wi-Fi access points that you can also upload. But this gives you an idea of what it does look like. And you can see all these access points and where they're located on the map. So you could line this up with your target environment, again, to try to determine, do they have Wi-Fi and what it's named and whether it's encrypted or not, right? Whether it's considered secure or not. So that's wiggle.net. Bluetooth is only becoming that much more popular in environments. I remember I just not too long ago, had a mechanic come look at my car. The battery died, right? And he came up and he hooked up one device to the battery, and then he connected to that device over Bluetooth from his phone, which would then give him the battery readings to tell him, yep, your battery is dead. It's the same thing in plants because you can have maintenance staff, right? Team members walking around and they can connect to different systems over Bluetooth, right? So you see a lot of different maintenance team members, right? Operators walking around using, carrying tablets, especially tablets, right? They're a lot easier, a lot safer to kind of carry around and use than trying to balance a laptop. And it's usually a bigger screen than a phone. I've seen people using their phones as well, but of course, I think tablets are kind of a good balance between the two, right? Easy to handle, but you have a much larger screen to work with. But there's a lot of vulnerabilities with Bluetooth as well, so we have to remember that those are there. That people can intercept Bluetooth traffic. You can launch attacks. You can have jamming for not for breaking Bluetooth, right? For denial of service attacks. Can you access systems over Bluetooth because it's unsecure, right? I mean, you inherit all of those vulnerabilities in a plant. Now, a lot of times you'll say, well, Bluetooth only works within, let's say, a couple of dozen feet, right? Or a couple dozen meters. But that's not always the case. And if you have the right equipment, you can actually get Bluetooth signals from a mile away, which is crazy to think of. So again, we have to stop thinking of like this, if you're not close enough, you're not going to be able to use that signal. So we're not going to have to worry about the security risk or vulnerabilities that come with it. Because again, that's not always going to be the case. I did want to also talk about wireless HART. So this is one of the more, OT wireless protocols that I like. And the idea is that we use it from a wireless perspective to create a mesh for sensors to be able to report information back to the rest of the OT network, right? To where they're trying to get the sensor data, like to our PLCs. I'm going to go ahead and jump to the picture here, which helps you understand a little bit more, right? I have these sensors, things like humidity, temperature, pressure, pH levels. And I have to get all this sensor data over to the PLC. But these sensors are located, we can say either, on the far side of the plant, or maybe there's a lot of steel work and there's a lot of pipes between where those sensors reside and where the PLC is. And it's too cost prohibitive, right? It just costs too much to run cables. So what we can do is we can have those sensors report in data over a wireless connection using wireless HART, which actually does have some basic form of encryption. And it sends the data to the sensor gateway. The sensor gateway collects the data from the sensors over the wireless connection, and then it's physically wired to the network that it shares with the PLC, so it can get the PLC the data. Now that's okay, all said and good. The really cool thing about wireless HART is that it also creates a mesh between the sensors, right? So maybe that pH sensor, right, there's a pipe between it and the sensor gateway. So it can't transmit directly to the sensor gateway, but it can transmit to the pressure sensor, and it can transmit to the temperature sensor, and it can transmit over to that humidity sensor. And then that they can actually forward that information on to the sensor gateway. So that's this idea of the mesh that it can create across those sensors to be able to gather that information, send it to the sensor gateway. The sensor gateway can then relay it to the PLC because the sensor gateway and the PLC are on the same network. So I think it's really cool how they've come up with this. And I've got to, see this in the field where, yeah, you have just huge steel beams or pipes, right, that are blocking the signal between a sensor and a sensor gateway. So you can have it essentially bend around those pipes and bend around those steel beams by sending that data to the other sensors, which then use that as a way to communicate with the sensor gateway. I like how we do routing on the internet, right? We have a route to get that data to the PLC. It's just not straight there. We're just going to have to take a couple of jumps through these other sensors. So that's wireless HART. I did want to include this slide. I actually found this slide in a presentation some time ago that Mark Bristow had done. Mark Bristow currently works at MITRE. So he heads up the Infrastructure Protection and Innovation Center that he does work. Like he just led the exercise working with the entire city of New York and all their entities to put on one big kind of war game or tabletop exercise. Right. So those are some of the types of things that Mark works on. But he had put this presentation, this probably goes back, I think, 7-8 years ago, but looking at the different pieces of equipment that you can use to capture wireless HART traffic. So definitely, I think you could build out an entire class, right, around wireless communication and OT, ICS, and the security vulnerabilities. Right? But I think, again, at a high level, again, for this course, it's something to be aware of and that we have to remember, especially with Wi-Fi being inherited from IT. We have to make sure, yeah, we're inheriting that Wi-Fi. Yeah, we're inheriting those vulnerabilities as well. So we need to make sure those are addressed just like we do in IT. Alrighty, so that closes out our section on wireless. Again, there's a lot there, but just for now, keep in the back of your mind, there's a lot of vulnerabilities. There's a lot of different ways attackers can take advantage of wireless communication that you have to keep in the back of your mind. Now, in the next part of the course, we're going to talk about operating modes, right? I love operational modes of controllers and PLCs. And this idea that systems, remember, when they're in run mode, we consider it the most secure of any of the other modes, which makes sense, right? And we've talked about this previously, right? When you're in run mode, the idea is that it prevents a remote party from putting a new version of firmware on that PLC. Right? So we're not able to put new firmware on the PLC. Now, a lot of PLCs will still allow you to make programming logic changes. It'll actually say, hey, you're trying to make a change to the programming language or the program logic that's running currently on the PLC. You're in run mode. Do you really want to make this change? And then you can say yes, and it'll actually make the change. Sometimes that's not always the case, but at least the ones that I had tested, and I typically try this anytime I get my hands on a new PLC. Of course, that's not in production. Yeah, I want to see, can I make changes to PLC programming logic while it's in run mode? Could I potentially try to put a new version of firmware on the controller? Again, that's one I haven't found yet. But again, all of them have an option to allow you to change the programming language, even if it's in run mode. Remember, if I look at a PLC, now this is the Click PLC. I like to use these because I see them in production, right? I love using them in labs because you can get a fully loaded Click PLC for $400. You can actually see that the run switch, right, or the switch for operational mode, it's real simple. It's a little dip switch. Right? You can kind of see right here in the middle. Right? It's this idea. It's either in run or stop. That's it. So it's either the PLC is running and is doing what it needs to be doing, or you've stopped it for programming, right? So that's when you can put new version of firmware. You can put PLC logic changes. Now, if it's in run mode, right, you can't change the firmware, but you can change the PLC programming. But that's the idea. Now, of course, more expensive controllers actually have a physical key switch that you would insert in, and you could actually turn that. And then, of course, you could take that key out and lock it up. And then maybe only the plant manager has access to the key. And then you would have to get the key from the plant manager before you would be able to take it out of run mode to make any changes. Now, for my master's project, I had this idea where I wanted to set up a simple web page that would allow someone in an OT environment, and it would connect to their different PLCs and determine whether the PLCs were in run mode or not. And then if you had a PLC that ever came out of run mode, which means it's going to be in a less secure mode, that you would get an alert that you would investigate. Because we want all of our PLCs in run mode. Because yes, it does mean it's in a more secure state. And so I used a couple of different types of PLCs that I had in the lab. One of them was the Allen Bradley or Rockwell Automation assets. I had a Micro 820. Now, it didn't actually have a physical switch like we just saw with the Click PLC. It was one you could either turn on or off in software, which we're going to see in a second, or you could buy like a $400 add-on component. Basically, that was just the switch for operational mode. I'm like, I'm not going to spend that money. But there were a couple things, what you'll see. I think there's some good examples, some things we've touched on through this course. And if you want, you can find the white paper at the link down below. And it was for my SANS Masters, so you can see the link there. But and here's one of the PLCs I had in the environment, so the Micro 820. It's kind of their kind of entry level model of PLC. But with the Allen Bradley, the Rockwell, right, you would launch their software and it goes out, right, and tries to find all of the different types of equipment made by their company. And so if you're on that network, and then you can see, oh yeah, here's this Micro 820. Here's the model, right, the make, the model. It's at 182.168.100.210. And here's the different components that make up that PLC. We can see it was running from the engineering workstation called New Laptop. Real imaginative, I know, but it was for the lab. And this is where I mentioned, remember, by default, that PLC doesn't have a key switch. Right? I don't have even that little dip switch to go from run mode to stop mode, but you could actually connect with the software, which did require a password. And then you can actually see, oh, there's a little button that says, oh, is it in run mode? Or you could put it in program mode. All right, we want to put it in program mode if we're going to put a new firmware on the controller. So as a technician, right, you would have to go in, know a password, and then be able to put it in program mode. And then with my paper, right, and the project I was working on, if you bumped out of run mode, then an operator would get an alert that says, hey, this Micro 820 PLC just bumped out of run mode. You need to investigate, see what's going on. Because we just want to make sure it's not an attack. Now, one of the things, of course, doing the project I had to understand was, or had to determine remotely, is that PLC in run mode or not? And initially I was kind of sweating bullets because I was like, I love this idea, but how do I do that? What I actually found out was if you use the nmap script, enip or Ethernet IP info, so enip-info.nse, if you use the script, it issues the command over Ethernet IP to request. Or it's one of those commands that just says, hey, tell me what you are. And you can see that the PLC comes back and says, hey, I'm a PLC. I'm a programmable logic controller. I'm made by Rockwell Automation / Allen Bradley. Here's my make, my model. Here's my serial number if you need to call support. Here's the product code. Here's the revision, the firmware version. And then you start looking at, status and state. Because if you look at that state, if it's set to 3, then, you're in run mode. Well, what happens if, though, I take it out of run mode? Then you can see the state actually changes to 2. In fact, actually, I think it would be program mode, not stop mode. So I made that, hopefully that wasn't in my paper. But the whole point for the project is I just want to know if it's in run mode or not. I don't care about the other modes, whether it's in remote program or stop. I just want to know, is it in run mode or not? Because if it's not in run mode, I need to investigate to see something's going on. And here's what it looks like if we're looking at that traffic in Wireshark and what that request looks like. Remember, we issue that request, and you can see it's called list identity request. And then we can see the response, which is everything that we just saw that was displayed in that Nmap scan. But that's actually the data that comes across in the packet. So there's a couple ways, right? You can check to see if a controller, a PLC, is in run mode. So you can look on the PLC itself. Most actually have a light that'll either be on or it'll be blinking, to show you, is it in run mode? Is it in remote program? Is it in program? You get the idea. And other lights to indicate some type of error condition, right? You can see there's whether we can have any IO activity, right? Do we have data or signals coming in the inputs, right? As if we have data coming in from sensors, or are we sending signals outputs to equipment out in the field? Right? If there's no activity, then it means that PLC is not doing anything. It's not in run mode. Right? So if there's no IO activity, I don't see any blinking lights on the PLC that would indicate any IO activity. Yeah. The PLC is not in run mode. More than likely. I guess it could be in run mode with no real logic, and it literally just sitting there on, but it's not doing anything. Of course, like we just saw, you could connect to that controller, to that PLC with the vendor software. And then you can go in to where you could see it to say, is it in run mode or not? And then you could connect to the PLC, let's say over Modbus, or in this case, we're talking Ethernet IP, and we can query data values in memory and watch for changes. If we're not seeing any changes over time, then PLC is probably not in run mode. And we can, again, depending on the protocols, I think there are 2 or 3 I focused on in the paper. So over Modbus, and then Ethernet IP, like we saw with Nmap. I think actually I also did S7 because I had a S7 1200 PLC. So that you could, right, there's different commands that we can issue to check remotely whether the PLC is in run mode or not. Right? And there's different Nmap scripts like the one for Ethernet IP that we just saw the example for. So in LabShock, we have an instance of OpenPLC, a virtualized PLC. And if you log into the dashboard, you can see the first thing it tells you, it's running. So we know in that case that it's in run mode. Of course, we also have the sample, like virtual PLC that we put together for the course. And then there was that gentleman that works at that sensor company that built it out to be a more realistic PLC for emulate a Rockwell PLC. And you can actually see now there's a PLC status tab. And you can see whether it's in run mode or not. And the cool thing about this is that you can see, again, that he created this to emulate how a real Rockwell PLC would operate is that a lot of times controllers, right, whether it's in run mode or not, can be controlled through things like coils. So what if I can connect to that PLC and I can flip a 1 to a 0 and all of a sudden now that controller is no longer in run mode? Or what if there's a register that allows me to do the same? So that's something that we look at later on in the labs, to have that ability to take a PLC out of run mode remotely. Well, that's not good. That's why I like the idea of having that web interface. So if you're in an environment, you can see all of your PLCs and whether they're in run mode or not. And if one bumps out of run mode, you get an alert and you know, oop, I need to go investigate. Like in this case, right? PLC goes into program mode. I need to investigate what's going on. Is it a PLC tech making some changes? Are those changes authorized or not? Or is it an attacker in the environment? But we have to keep an eye on those controllers. So we have to also, be aware. Do you have a PLC that an attacker could connect to over a OT protocol like Modbus, Ethernet IP, S7? Make a change to a coil register to be able to take the PLC out of run mode and put it back before anybody notices. So that's what we're going to go through in Lab 6.7. So you're going to go through those steps that we were just looking at. Of course, in this case, using all the simulated environments that we have between LabShock and the simulated Rockwell PLC that we have for the class. But you would do the same thing. You would take the same steps with real equipment in the real world. Again, that's Lab 6.7. When we talk about manipulating I/O image, remember when we say I/O, we're talking about inputs and outputs. Remember, inputs are the data we have coming in to a PLC, in this case, from sensors. And then the outputs are those physically wired channels that we use to send signals to equipment in the real world. And so when we talk about manipulating I/O image, what we're talking about is connecting to the PLC and making changes to the data that reflects the state of those inputs and those outputs in memory. So that's where, and we've started to have some examples of doing that, right? So we're not going to spend a ton of time here because, we've been doing this throughout the course, and there will be some other examples that you'll work through as you go through the labs, and that includes working with the LabShock environment. But can an attacker connect to that PLC over an unsecure OT protocol like Modbus? Remember, it's unauthenticated. We're not asked for a username or password, and we can issue it commands, and it'll do what we tell it to do, which primarily is read the values in memory and then change them. Now, we didn't get into too great of detail when we talk about the PLC scan cycle previously, but we saw this. Like that, the idea is that, remember, we start off with the input scan, right? Meaning we bring in the data from our inputs, right? So the data we have for the sensors, right? If go back to the thermostat example, right? We're always continually, let's say every second, bringing in the value of the temperature that's read in the room, right? We're bringing that into the controller. So we bring in the data through the inputs. Then we actually run the programming logic on the controller itself, right? So we go through the program scan. So we go through and we run the logic. Remember that thermostat, we had logic to say if the temperature in the room is higher than the set point, turn on the air conditioner. So we bring in the temperature from the sensor, right? The input scan. Then we go to run the logic to say, hey, if the temperature in the room is higher than the desired temperature, the set point, turn on the air conditioner. So we had logic then that triggers turn on the air conditioner. To turn on the air conditioner, we have to send the signal to the air conditioning unit via the output. So that takes place during the output scan. So we have input, program scan, output. And then we'll go through housekeeping. In housekeeping, we have a lot of like diagnostic type activities that happen, and really making sure not only that the controller is working, but that the systems that the controller is working or is communicating with is working appropriately. And we'll come back and we'll talk about a little bit more details of that later on. I think that's the PLC, right? Is essentially stuck in this loop where it goes bring in data, right? Make sure that it runs its logic using based off of the data, has results, right? If it needs to make changes in the real world to our equipment, to the process, it'll send signals out the outputs. And then just checks to make sure, yep, everything's working appropriately, and then circles back and does it all over again. So that's the PLC scan cycle. Now, when we look at the PLC again, we've started to touch on this, but when we connect to a PLC, let's say as a pen tester or as an attacker, when we first get access to the network, let's say we connect to that PLC over Modbus, and we start reading coils and registers, we just see numbers, right? We just see zeros and ones or other numbers, right? We see those values. So if we look at the essentially, if you want the table of data in memory that we see here, like on the back end, right, when the developer actually programmed that controller, they assigned names or tags to each of those values in memory that we can read and write from, to and from. So I can say, oh, okay, that first coil is for the emergency stop. That second coil is for a guard door lock, right? So it's for a safety control. Right? You can see motor overload FLT. So we could probably start to guess, right, what some of these values actually mean if we can get those tag names. Now, sometimes you see something like thingy one. Like, well, what the heck is that? We don't have any clue. So from a programming perspective, yeah, it's great to be able to give these tags, right? To give these tag names that actually mean something, right? And can tell us what those values actually are related to. I guess from a security perspective, sure, something anonymous like thingy one or thingy two, that's great. But from a coding and a troubleshooting perspective, that's obviously not. So I'd much rather see real, meaningful tag names. Pressure sensor low, fill level high. Remember, when we connect to that controller over OT protocol like Modbus, right? We're just seeing the zeros and ones, or the for the coils or the registers, right? Higher values. We don't actually see the tag names. We have to find the other tag names in other systems, whether on the engineering workstation or on a data historian. But just keep it in the back of your mind that, yeah, those zeros and ones, they do have associated tags. You just don't see them. But if you did, I think it would make life a much easier on you, right? As a pen tester or as an attacker trying to reverse engineer the environment to determine what's going on. Of course, we've already started to see some examples, and we're going to get into more examples as we go throughout the rest of the course, because we can manipulate those values in memory to do things like, yeah, create false sensor readings. Very similar to or Stuxnet, or the operator sitting in the control room and everything looked perfectly fine, even though behind the scenes those centrifuges were physically breaking down. Well, if we can send unauthorized outputs, right? Signals to make changes in the real world. So yeah, and lab shock, and there's a couple other examples that we have in the class. What if all of a sudden, yeah, you do turn off that? Let's see, the motor in the air conditioning unit, or what if you turn on or off a pump, or open or close a valve when you weren't supposed to? And if it's a specific time within the overall process, what is the impact going to be? Is it really, oh, nothing really happens? Like, oh, okay. Maybe if it's super early on in the process. Maybe if, a couple, I don't know, 10% later into the process, if we turn off close a valve, it means we spill, I don't know, let's say 20 gallons of water onto the shop floor. Okay, not the end of the world. But then maybe, 50%, halfway into the process, if we make that change, all of a sudden now we get into a position where we've ruined an entire batch that we're manufacturing. And then that has to be completely scrapped. And then we can look at, well, how much did all those resources that we're using to make that batch cost? And they can all be just flushed down the toilet. But I always do keep Stuxnet in the back of my head because, sure, that we always say is a state adversary, right? And the best of the best. But it's not that hard in most environments to pull off that same attack these days, where we can hide our activity from those that are sitting in the control room. And like I said, we'll have that in a couple of different labs we'll play with. Now, how do we make changes to the memory running and the PLC? Right? I think we've already again done this a couple of times through class. Now you can use the software that comes from the vendor that allows us to interact with those systems. Or again, we can connect over one of those unauthenticated OT protocols like Modbus to make those changes. No username, no password. Usually when you use the legitimate software, there's usually at least a password involved. Now I see a lot of default passwords still in OT, and if you haven't changed it, like I think that if I remember it, the default password for the Click PLC is Click. Makes sense, right? It's probably the one you would guess. So if you don't change the password, right, default passwords are still a thing, even in OT, right? We see them everywhere in IT, and we see them everywhere in OT. Or in this case, like in Lab Shock, right, we have our HMI. We're looking at the environment. And Lab Shock was built using open source tools, but where you can actually go into, and this is the Open PLC backend. And so you can see not only the data, right, the labels or the tags that we were mentioning earlier, right, like pump 1_start. But you also have the ability to actually click false here to send a 0 to that coil, which then, as we saw previously, will turn off that main pump, turns off pump 1. And then if we scrolled further down the list, we would see pump 2 start. So when it's set to 1, the pump's on. When it's set to 0, the pump's off. So you can do it through the legitimate function, like in this case, the interface, and I can just click true or false to turn it on or off. And if it goes false, the little green button turns red. But we go back from, turning the pump on and off, like we did in one of the previous labs. That's why we're just not taking the time to go through it here. So there you can see, click false, boom, they turn off. And then this is where you go back to the HMI. It's like, oh, okay, yeah, the pump's no longer on. Right before it was green, Now it's red. Right, so we have that visual indicator. And then in the upper left-hand corner, you can even see, oh, okay, yeah, both, in this case, both bumps are down. Of course, we can also connect over Modbus, and we could use tools like the Swiss Army knife or any of the other Modbus utilities you have out there. In this case, though, you can see we use the option. I'm just going to say I'm going to overwrite that very first coil. Remember, zero based. So the very first coil is number 0. Take that first coil at number 0 and set it to 0. Boom, the pump turns off. Again, that's pretty easy. It doesn't always work like that, but it can, and it does work like that. I guess, I don't know, let's say even half the time. Remember, it doesn't have to be too complicated, and attacks don't have to be any more complicated or complex than they have to be. Now we do create, and there's a walkthrough in the labs where we create our own version of Frosty Goop using ChatGPT, and I called mine Snow Crash just to use a different name. Now the attackers, when they actually just converted it to an exe, so it was literally modbus.exe. In this case, I called it Snow Crash based off of one of my favorite books. It's a cyberpunk book if you're into that type, kind of like William Gibson and things like Neuromancer. But you can see the command syntax that they used. It's not very pretty. It's kind of ugly. But in this case, right, I'm just using a Python script to simulate Frosty Goop. And so the lab will walk you through, right, the process of, okay, how would we turn off like that first pump using Frosty Goop syntax? Or how would we change the temperature or the flow of oil through a part of this plant by specifying the IP address, and then there's mode, basically read write, and then the address, right? What are we changing the address in memory, right? Which coil, which register, essentially, and then the value. What do you want us to change the value to? So actually go through that in one of the labs, doing that lab shock walkthrough, but using a tool that simulates Frosty Goop, again, which was created by these state actors. But you'll see, like, again, we can recreate that in 5 minutes in ChatGPT. It's not that difficult. We're not talking about complex, and we're not talking about complicated, but they used Frosty Goop to create a 2-day heating outage in 600 apartment buildings in the middle of winter. And so you can see there's a couple of different scenarios and examples that you'll go through. And here's another one for using Frosty Goop, right? Which command would you use to change the inbound pressure on the oil pumping station? Now, one little trick, and the lab will walk you through this as well, is that the Kali Linux instance that comes with LabShock, right? And you can SSH into it. Remember, it's essentially kind of isolated on the LabShock network, and it's also connected to your network. But there really isn't a super easy way, right, by default, just to copy and paste our tools like the Swiss Army knife or Snow Crash and put them on the Kali Linux instance. So here what you do is you actually create a web server. In this case, you can see there's 2 examples here. Let's look at the second one, right? So we can use, and this is just a built-in function within Python. So you can run Python with -m and say, run a HTTP server. So it creates a website or a web server for you. We're going to put it on port 8888. So we don't want anybody connecting to it on accident, right? If we put 80 or 443. And then the website is going to make available the files in the C scripts directory. Cool, right? So on my Windows machine, or on your Windows machine, you're going to run this Python command to spin up a web server, and it's going to serve all of the files in your C /scripts directory. And then from your Kali Linux machine, you're just going to connect to the web server and download the files. And you can use a browser to do that. Or here, you can just use wget. Now, wget isn't installed on Kali Linux by default. So you can install it first by app install the -y just to accept all the defaults, wget, and then wget, and then the URL for like the name of the file you're trying to download. Like in this case, you would download the modbus _ Swiss Army Python script. Hopefully that makes sense. There's other ways to transfer, but for me, I think that's one of the easier ways. I have Python on the Windows machine, just spin up a web server, serve up those files through the website, and then just download them from the Kali Linux box. And then once they're on the Kali Linux box, that's where you can go ahead and you can quote unquote attack LabShock using those tools. But that's what you're going to walk through in Lab 6.8, including even the part of creating your own Frosty goop using ChatGPT, or you can use whatever Gen AI platform you want. I just typically tend to do everything in ChatGPT since it seems to be the most approachable. So that's Lab 6.8. Now, when we talk about reverse engineering or understanding not only the environment, but the process itself, right, and the equipment that we're controlling out in the real world, we need to be able to be in the situation where we're in the environment and watching over time for changes, right, that are going to help us better understand how the process actually works, right? How do all these components come together to do this thing that we have in the environment, like generate electricity? So we'll go through some examples of types of data that we can be looking for. Things like, values from sensors over time, actuator states, what happens with those pumps, right? Are they turned on, off? Is there a correlation between sensor readings and those actuator states, like when a pump goes on and off? Do we have alarms that trigger, right? And other types of information that we can see, right? So a lot of this we can see from, what happens if we got access to a historian? Think of all the data that could be sitting on the historian and how it could be useful from an attacker's perspective or a pen tester's. I guess I already gave away the answer to this. Because we have a lot of this. Yeah, we send it to the data historian. Remember, the data historian kind of acts like that SIM. It's that central point where we can bring in all that telemetry data and store it in a central location. So again, we can watch over time how different parts of the environment operate. Again, when we're first connecting, right, we're just seeing numbers. Those numbers don't have any meaning. But little by little, right, just like building that Sudoku puzzle, little by little, we're starting to put the pieces together. We're starting to understand how the environment's designed, how it's engineered, how it operates. And we don't have to understand every aspect of the environment to have an impact. But the more we understand, the more successful we'll be. But this is where especially we're bringing in our own engineering teams to understand in the environment what could happen. Now, most pen tests, right, have already stopped by this point. Right? They might want to see, hey, can you get on a data historian and access the information there? And if you can, boom, you're done. So this is more from the attacker perspective. And this is why attackers are sitting in OT environments for so long, because they have to take the time to reverse engineer the process, right? To understand how it's designed, how it's engineered, and how they're going to make a change in the environment to have that impact. That's why, yeah, we need weeks, months, years. We could say, sure, Gen AI or AI is going to shorten that window. Sure, it is, no doubt about it. And that window is going to get smaller and smaller and smaller. But they're going to still have to take some time, right, to get in the environment, to map it out, right, go through discovery and collection, and then have that data to be able to ultimately reverse engineer the environment. Of course, we can pull the data directly from different assets as well. So what if I don't have access to the data historian? Maybe they don't have a data historian. I've seen that. So some environments, they might not actually have a data historian. So what if, okay, maybe I just want to connect to that controller. Maybe I don't want to try to even break into a data historian, which maybe there is some additional security monitoring there that I don't want to trigger. So I want to go ahead and be able to connect and watch for changes over time. Now, if the defenders are watching from a network security monitoring perspective, and all of a sudden you start connecting to a controller and reading values from memory, right? You're issuing Modbus commands for reading at least. That should set off alarms. But that's a big if they're doing network security monitoring. Again, remember, only about 5% of OT environments are actually doing network security monitoring. And probably half of those are doing a really bad job. Here's one tool I created in ChatGPT. Because what it'll allow you to do is it will allow you to connect to a controller over a Modbus. And then it pulls just once a second. And you can see you can change the polling duration. So maybe we want to say okay, every half second. But you can see here that we're pulling that data and it's writing it out to, yes, we see it displayed on the screen, but it's also writing this all to a CSV file so I can pull it later into a tool, even just something as Excel. And I can look for changes over time. Again, I'm starting to help reverse engineer the process. Of course, this should look familiar because this is the virtual PLC we use for the thermostat example. So remember that fourth coil when it's number one, that means the air conditioner is running. And the air conditioner is running because remember the temperature that we see over on the right-hand side is inside the room is 74 degrees. And it's higher than the set point of 72 degrees. So we want the air conditioning to be running to cool down the room or the warehouse or the whatever we're cooling with this air conditioning unit. And we can also see there's a slight fluctuation between the temperature because it goes between 74 and 75 degrees. So that would be one fluctuation that we could see over time. And then, dump it into a tool, whether it's like Excel or Grafana, throw it into the cloud if you're not worried about confidentiality, right? To look for changes over time. And here you can see, right, we're just pulling it into Excel, and then we can make all the graphs that we want. Now, I also created a GUI version, and I like the GUI version because it allows us to see much easier, like in real time, what's going on, right? Now, what you'll see is it's only showing like 3 values where before, and this is connected to the same PLC, right? Before we had I don't know, like 20, 30 different values that we were tracking, probably 20, let's say. Here we're tracking 3. Well, if you try to do like 20 or 30 in the GUI, it can do that, but it gets really ugly really fast. So what I told ChatGPT to do was when it created this, right? Only start with those coils and registers that aren't set to 0, right? So at this point, we assume everything but coil 4 and register 5 and 7 are zeros. And if you're familiar with that thermostat example, yeah, that's exactly what happens. And then if any of them change, then start recording for that coil or register. And even if it changes back to 0, keep recording. So you can watch it over time, like with that bottom register, right? We can see, oh yeah, there's that fluctuation in temperature where it fluctuates between 74 and 75 degrees. Again, it allows us remember, as a pen tester or an attacker, when you first get in the in the environment, you just see these numbers, right? And without an HMI, just seeing a bunch of zeros and okay, there's this, these ones in column 4, right? And we see 72s and 74. Oh, but it fluctuates between 74 and 75. It's all part of trying to reverse engineer the environment. And there's a later example where, yeah, you'll start looking at these numbers. You're not going to have access to the HMI. You're just going to start looking at numbers and then see, right, how you can build the Sudoku puzzle, right? How do we reverse engineer and slowly figure out, oh, okay, this is what's really happening in this environment. So yeah, that's the Modbus to GUI Python scripts. Like I said, I like it. I think it's really cool and it's helpful. So, but where we can watch again over time what's happening in the environment, look for those anomalies, and then we can line them up again as a way to reverse engineer what's happening in the environment. And that's what you're going to do in Lab 6.9. So you're going to use all these different tools that we were just talking about, and you're going to have some lab data to play with. Again, use that to walk through a couple of examples and reverse engineering the environment. So that's Lab 6.9. But I definitely have a lot of fun with that. A lot more than I ever thought I would have. But it is a lot of fun to actually watch that environment, watch for those changes, identify those anomalies, and then start to, again, use that to reverse engineer what's going on in the environment. So in the next part of the course, I did want to talk about, and I've mentioned this before, where we talk about, we do have data historians. Remember, data historians, and there are other different types of systems in OT like HMIs now that run as web applications as well. Wherever you see a web application, you have to remember that web application itself has its own vulnerabilities that you can use to compromise the web application, which could give you potentially access to the underlying web service or the underlying operating system. But the web app can have its own vulnerabilities, right? That web application, it runs on a web service, a web server. And that web service, it has its own vulnerabilities. And that web service, right, runs on an operating system. That operating system has its own vulnerabilities. And for a data historian and some websites, right, on the back end, there's a database. So that database server has its own set of vulnerabilities. So we inherit, of course, a lot of these from the IT world. But the point is, if you have an asset like a data historian or an HMI that's presenting the interface as a web app, you have to remember there's vulnerabilities in the web app. There's vulnerabilities in the web server the web app runs on. There's vulnerabilities in the operating system that the web service runs on. And then if there's a database there, yeah, the database has its own vulnerabilities. So from a security perspective, right, as defenders, we have to make sure we're aware of these vulnerabilities and addressing them as needed. As pen testers and attackers, we just have to remember we have all of these different angles that we can approach, right, with vulnerabilities to see, could we use any of these for access? And it's not just web app vulnerabilities, it's all of those that we could potentially use. So you don't want to end up like the poor data historian system administrator here. We want to make sure we address all of those vulnerabilities. The nice thing, right, is most of these systems are running Windows. So we could be patching at least most of these on a regular basis. So we do want to keep them up to date. Just remember, we have to work with operations. We have to work with the engineers and make sure that when we're doing those upgrades, that we're not introducing safety or operational availability issues. But we have to make sure, right, we're defending all of those layers. Or as pen testers, right, we're attacking each of those layers. Now, going back to the idea of the data historian, I wanted to look at a kind of a brief sample that put together of, hey, if I got onto the data historian, what would I see? Or there's a couple things that we see from the data historian perspective. What I'm always looking for is that essentially what we see here is that top row. Looking for those tags, those tag names. Remember, the tag name can actually give us the kind of the intuitive name to tell us what are we actually looking at. Like when I see a value like 1.53936, like what's that? It's like, oh, okay, that's the pressure, the barometric pressure in this reactor vessel. It even tells us, ooh, there's a reactor vessel in this environment. And so we have the timestamp of when that data was recorded. You see the data itself, and then or you can see the tags, which can help tell us what each of those values means. And then we can use the data to look over time as the process, right? There's changes in the process. And we can use tools like Gen AI to help us do this nowadays. Or even just if we're visually inspecting this, right? If I look at that heater output percentage, right, it's kind of like 61, and then it starts to drop, and then it boom bottoms out. It's like, that's interesting. Well, is there some type of correlation we have to some other change in the environment? That's what we're trying to do, right? When we're reverse engineering the environment. This is kind of a later example kind of build off of this, because I'm also always looking for, like on those last two columns, like operator mode, safety trip. I'll make sure we don't have any safety issues. Right? And then in this case, right, everything, right, the controller, right, and the HMI, or the the controller itself is handling everything. Right? If there's any changes in the environment, the controller is doing that. We didn't have to have a human operator come in and take over or make changes. Awesome. Though we have to ask our questions. Well, what if the operator mode comes out of auto? Or what if there is a safety trip? Those are some of the big questions, right? We have to start asking. All right. So as we start to wind down this part of the course, we started mentioning earlier, another attack vector for an attacker. I think if I'm in the environment and I find a controller, what if I have the ability to upload or put my own PLC logic on the PLC itself? This is where we talk about downloading the program logic to the PLC. So one moment the PLC is running good code that somebody had programmed. Maybe the integrator or the vendor or PLC tech had programmed onto that controller. And then here we come along, and maybe someone left the PLC in remote program mode. And for that particular PLC, that actually allows me to update the PLC logic. Or maybe it's even in run mode, right? Most PLCs will still allow you to change the programming logic if they're in run mode. So if an attacker gets in the environment, they have that ability to put their own PLC logic. Now, a lot of times, what if they can find a copy of the code running on the PLC? Like, think of where we could find that, right? First place I would look is right the engineering workstation. And if I couldn't find it on the engineering workstation, then I would look for on file servers and look for backup locations. But what if we can find that current programming logic that's running, and then we can review it, we can read it, and then we can make just slight changes to potentially have an impact, and then we can put that on the PLC. And now we have the PLC running our code, right? The bad code. And maybe the operators don't even see anything wrong, and maybe nothing happens right away. But it's sitting there waiting to that point in time where we are going to choose to trigger it to have that impact. So ultimately, right, we can, again, and we'll go through some of these examples later on in the course. But yeah, why do we want to put bad code on a PLC? Well, okay, if I'm a pen tester or in a test environment, or if I'm an attacker, yeah, we can alter how that process operates. Even just the slightest tweak, right? Think of I always go to pharmaceutical, right, manufacturers. If I can make the slightest tweak to the process, then all of a sudden you have massive failures in creating, let's say, those insulin injections that are going to fail in QA. And then all those resources we spent making those injections, right? They go in the trash, or they have to be physically destroyed. So there's a couple of different ways that we can do this. So yeah, we can introduce malicious routines. Again, maybe that the operators don't even see right away. We can take things out. So I was gonna put examples in this course, and then I started to build this out, and you'll see. And then I realized, well, to get there, we have to also take time to understand, well, how do we program PLCs using languages like ladder logic. And then I decided, well, that has to be like an entire whole like separate workshop. But if we have attackers, or what if it's just a PLC technician, right, in the environment making changes that aren't authorized, right? How are we not catching this? And operators, they're not checking the integrity of the files running in memory. So think we can just like a file where we can have a file hash or a checksum to tell us, is this good or is this bad? We're not doing checksums, right? We're not doing integrity monitoring. At least most environments are not. And most environments, right, unless typically they have, a great, one of the network security monitoring platforms like a Dragos, Nozomi, Clarity, right? They're not monitoring the operational modes of their controllers. So they don't know if a PLC was to come out of run mode. Again, that's for more on firmware changes. Remember, most PLCs will still allow you to make, unfortunately, program logic changes, even when you're in run mode. Again, just keep in the back of your mind, right, the PLC scan cycle, right, bringing in the data, running the logic. Now, right, what if we've manipulated that logic, right, which then, remember, then could be used to manipulate the outputs, which is what we use to control the equipment and the process in the real world. So it's all about what are we doing here in the program to ultimately have that impact in the real world. Are we sending new commands, essentially, right? Signals through the outputs. So we can take a step back, and this is kind of building into that workshop that I wanted to build out. It's next on my list, where I talk about, well, how do we program a PLC? Because if you've never actually had a PLC and connected to it and programmed it, right? Well, you wouldn't know, right? It's just not something that you've done. So you can do it over the network, right? From an engineering workstation. Right? There's maybe like our Dell laptop at 192.168.1.10, and we can connect over the wire. If that PLC is configured to allow remote connections to come in and program, and here you can see it's at 2.103. Of course, that's where we get a lot of risk from a cybersecurity perspective, because if that operator can connect to, or the engineer can connect to 2.103, what if there's an attacker on that network? They can probably connect to 2.103 as well, because most OT network, even when we talk about secure network architecture and making ACLs as restrictive as possible, it's not as common to see, unfortunately. Or, and this is the more secure way, you have to have an engineer or a tech, right, walk to where the PLC physically is and then connect to it with a cable. That's the most secure, right? Because if there's no remote network connection like over Ethernet and TCP/IP, right, the chances of it being hacked, right, by a remote party is slim to none. But yes, doing the local connection, yeah, that's inconvenient. And if your PLC tech is in California and your plan is in Canada, that's really inconvenient. And what if that controller is sitting in a really unsafe part of the plant? Do we really want somebody to take their laptop into that unsafe area and plug in just to make a minor PLC programming change? No, of course not. So that's why we want to allow changes over the network. But we do have to realize that's where a lot of our risk comes from. Now, how do we program those different controllers? You have to use the software that the vendor provides. This is where it always gets interesting, because let's say, okay, yeah, here we have 4 different types of, assets in the environment. We have 4 different pieces of software we're using. And they all kind of have the same function, right? Or functionality, right? They give you the ability to not only program their specific asset, but they almost always have the ability to find all of the different types of assets from their company, right? Which is great if you had all of one type of asset, right? But if you had even just 4 different vendors in the environment, you have 4 different pieces of software. And sure, Siemens can find Siemens equipment, and Rockwell can find Rockwell equipment, and Click can find Click equipment. You get the idea. But you can't use, any of these to find the others, and you can't use these to program the others. You have to use the software that comes with it. And I love Click because not only are those great little PLCs, but their software is for free. If you're looking at Siemens, like their totally integrated automation portal, right? Ps, I think the cheapest license is like $1,500. But you're going to connect over the network or through a cable using the software that you get from the vendor. Again, it's whatever the vendor provides. And this is where I started to go down the road of talking about what is ladder logic and how we program controllers. And I realized this is already a 4-hour part of the course, now broken into 2-hour pieces, basically. Like this has to be a whole other 4-hour workshop where we talk about what is ladder logic, right? We're simulating kind of bringing in electricity on the left-hand side, right? And we read it top to bottom, left to right. And you start to get, I see inputs and outputs, right? And it's like, oh, okay. we've started to talk about inputs and outputs, right? As we bring in data, as we send signals. But the idea is, yeah, understanding how we again, ladder logic's the most commonly used programming language for controllers. There are others out there, and there are others definitely gaining traction. And depending on who you talk to, ladder logic, isn't going to be the number one programming language of all times. But this is the focus on ladder logic in the workshop because it is still the most commonly used. And I do like kind of the thought process and putting the kind of the examples and scenarios together. If you look at LabShock, which we use right for a portion of our labs in the course, it's the open PLC is actually programmed in structured text. But for the side workshop, we're going to do ladder logic. And then maybe one day come back and look at structured text, or maybe take a brief look at structured text and some of the other ones that are out there. But it's all about understanding, kind of thinking through, the flow of electricity and it's like, we do, we turn on the switch and it allows the electricity to flow to where it gets to where, it turns on the light. And so I have a lot of fun with that. But again, it's a whole other thing. I can see, in the SANS world, Rob Lee, Tim Conway, and Jeff Shear, they build out an entire one-day course. And I think, 2 or 3 hours of that is PLC program ladder logic. And I'm like, it makes complete sense why. It's like, because you want everybody to understand. And like, I'm familiar with it, right? I've used it at a low level. I'm not considering myself a PLC programmer. But it's one of those, like, do you need to, I don't know, understand Java to be a, IT cybersecurity professional? No, you don't. But it helps if you can read it, right? And it's good background information to have. And if you understand like programming concepts, it does help you be a better, IT cybersecurity professional. It's the same thing in this case. You don't need to understand how to program PLCs to be an OT, cybersecurity professional, but it will help you do your job better. And if you ever got into incident response scenarios, and then you definitely would need to know. But again, so that's going to be coming soon in the new year. So keep an eye out for that. So again, thanks for watching. I really appreciate it. And there's a lot for these last two sections to make up that one part in discovery and collection. It's just there's so much there. A lot of the rest of the parts of the course will go much quicker because we spent all the time here. So thank you again, and I'll see you in the next part.